Hey, all right, let me try another video solution. This is number 60 out of chapter 37. Let me read it here. Number 60 says, a plano and convex lens has an index refraction of n. I'll pause there because I printed up the picture. So this is the lens they're talking about. So there's the plane one with the convex. So there's the plano convex lens. It has an index of n, so I suppose I could kind of point to it and say, okay, there's the index n. The curved side of the lens has a radius of capital R, so that's the center of curvature of this convex part. Let's see, it goes on to say the rest of the flat glass surface has the same index, or it rests on a flat glass. So this too has an index of n. Okay. On the with a, let's see, how does it phrase it? It rests on a flat glass surface of the same index of refraction with a film of index n between them. So this little area in here, and then likewise over here, although I don't want to color that one in, this area, and I guess it would also be then this area, is filled in with an index of n, and then they put a little subscript film under it. So kind of looks like in this picture I would just think it's air, but it could be like submerged underwater. So whatever this separation is would be the index of it. Okay, but then it goes on and it says as shown in the figure. So here's the figure. The lens is illuminated from above, so here is the beam of light coming from above, of wavelength lambda. Okay, so here's some wavelength lambda. Show that the dark Newton's rings. So these are called Newton's rings, and I didn't print up picture B, but picture B kind of shows a photograph of Newton's rings. And they are given by approximately this radius. So that's the little r. So out here some distance, little r, there would be a dark, and it would go all the way around because that would be the same thickness. And so they say it is approximately equal to the square root of some integer times the wavelength times the radius of curvature divided by the index of whatever the film is. So if this is in air, that would be 1. If it was submerged underwater, that would be 1.33, or whatever the material happened to be. Okay, now that's our goal, is to show that. But this is a thin film. And so let's say that we're looking at this light that goes down and back, and we call that a thickness T. And if you didn't quite get this out of the reading, let me show it to you again. But I like to do this. I like to say the extra path length, so delta, of the beam that goes down and comes back up. So they're kind of labeling it as beam number 1 compared to beam number 2. So beam number 1 travels an extra distance of 2t. And then if that is an integer number of wavelengths in the material, so that would be in the film, okay? Then my first reaction is to say I would have constructive interference. And that would mean the other option, where 2t equals to m plus a half, equals to the wavelength divided by the index of the film, would correspond to dark. Now, I'm not done, because that's what I would get only for the extra path lengths, and these would be maximum and minimums. But as I was trying to point out, these are a little harder because you also have a phase change. Okay. So grabbing a different color here and saying, all right, is there a phase change when beam number, and I'll do 2 first, beam number 2 bounces off of the film? And that all depends. It depends if the film is greater than. So if the film has an index greater than n, then the answer is yes, there is a phase shift for beam number 2. But of course, then watch this. Beam number 1, which comes down and bounces off this lower one, would not have a phase shift. So 1 would be a yes, and that would be, I guess, I'll put a little beam number 2, there would be a phase shift. But for beam number 1, there would be a no. Now, of course, the other option is that the index of the film is less than the glass. So if that's the case, then beam number 2 does not have a phase shift. See, number 2 is in the higher index and it's bouncing off a lower index. So there'd be no phase shift. But beam number 1 would have a phase shift. So it doesn't really matter whether the index is less than n or greater than n to realize that one's going to have a phase shift and one is not. Now, there is a difference of which one has the phase shift. But when it goes to figuring out the correct formula for are they bright or dark fringes, we only need to consider the comparison between the two. And since one or the other undergo a phase shift, we could say no matter what the conditions of the film are, one is going to have a phase shift and the other is not. And so what that means back up here in this equation is that right here where we were saying, okay, if the path extra length of number 1 is an integer number of wavelengths, we would get constructive. But because one undergoes a phase shift and the other doesn't, they would not meet up with maximums matching maximums, but one would shift and a maximum would meet up, or a crest would meet up with a trough. And you wouldn't get bright, you would get dark. And the same thing could be said here. So that extra phase shift reverses the roles of these. And so, again, the way I like to do these thin films is to take it back to just an easy case about adding them in terms of the extra length. Are they in phase or out of phase? And then say, well, how would I modify that with the phase shift? So in this case, I would modify it by changing what would have been a maximum to a minimum, because, again, they would have been like this, and then one shifts on me. And what would have been a minimum, so they would have lined up like this, and then one shifts on me. And so this is the equation for maximum, and this is the equation for minimums. And since this problem is saying, where are the dark rings, then I want the one that's saying minimum. Okay, so here's the one I want. These are minimums. And by the way, these are minimums on reflection. If had this been a problem with somebody looking from the underneath side, then we'd be looking at the transmitted light. And then these would switch roles. And so the equation for the transmitted light would switch roles. But that's not necessary for this problem. We just needed to figure out for reflected light which one was a minimum. And that's the right equation. And for so all these thin film ones, that I think is the hardest part here, is to recognize which equation should be used. All right, so now that I know which equation is the right one to use, let me put here that the thickness, where I will get dark ones, would be an integer times the wavelength divided by the 2 and divided by the index of the film. Okay, so that would be the thickness, and so that's that T right here. Now I'm going to do a little geometry to kind of finish up the problem, because that means this vertical leg of a right triangle, this one here, would be r minus t. That's that thickness right here. This thickness would be that right there. All the way down would be r, and if I subtract t, I would get this leg. And then going out perpendicular from it would be that leg, r. And the sum of the square of the legs equals the square of the hypotenuse. And now if we multiply this out, so we'll FOIL this out, this will be an r squared minus 2rt plus an r squared, little r squared, and a big R squared. And so the big R squareds cancel off. If we put an r squared by itself and move this over to here, we get 2 r and a t. If we take the square roots of this, we get the square root of 2rt. Now, if we take the t in here, so we've got the 2r, and the t is the m lambda over 2, and then the index of the film. The 2's cancel off, and I think we got the answer. We got an r, we got an m, and we got a lambda. That's okay, the numerator. And in the bottom, we've got the index of the film. Yay! So there's our answer.